You think your server crashes because you need more storage? It actually fails because of memory bandwidth limits and rigid security checks that ignore how CPUs and GPUs talk to each other. When a new AI model drops, the question that matters for most teams is not whether it has infinite context features. It is whether your stack can run it reliably without choking on data movement costs or crashing when hardware instructions don't match expectations. Today we connect that headline to the engineering trade-offs behind the hype and why naive RAG implementations break at scale. The failure of so-called enterprise memory governance layers is not a software bug waiting for a patch. It is a collision between architectural assumptions and physical reality. Many teams build systems assuming every server has uniform capabilities, treating missing hardware features as binary failures rather than performance trade-offs to be managed. Consider the case where an AI agent crashes instantly on startup simply because it cannot detect specific CPU instruction sets like AES-NI encryption support. On older processors lacking these instructions, the system does not degrade gracefully or offer a fallback mode. It terminates the core agent immediately, rendering all features unusable until a complex virtualization layer is added to pass through host instructions. This is an architectural failure where software expects hardware uniformity that simply does not exist in heterogeneous environments. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The problem deepens when we look at local development and latency requirements. Naive implementations of AI assistants often become unresponsive under load, specifically during interactions with database editors or chat interfaces running inside containers on common operating systems. The system hits a wall where memory bandwidth cannot match the request rate required for real-time interaction. It is not that storage capacity is insufficient, it is that data movement between the CPU and GPU saturates the available pipes. When you try to feed an AI model more context than its memory hierarchy can handle, the latency spikes until the connection times out or the process hangs entirely. This proves that scaling a system requires understanding physical limits of VRAM bandwidth rather than just adding more disk space or RAM modules. Governance layers intended to secure these systems often become brittle bottlenecks in their own right. When strict security checks are implemented without flexibility, they can turn minor configuration mismatches into immediate service disruptions. In some instances, users attempting legitimate requests were banned after a single failed interaction because the assigned model was not on a rigid allow list. The system interpreted this as an attack rather than a misconfiguration error, blocking access entirely instead of handling the mismatch gracefully. This highlights that governance layers must be designed for dynamic hardware realities where models and resources shift constantly, not static rule sets that assume perfect alignment between software logic and infrastructure state. Successful scaling requires moving away from mutable configurations toward immutable setups that respect these physical constraints. Architects are now enforcing fixed directories to prevent drift in data paths and disabling persistent connection protocols like HTTP keep-alives on constrained hardware to reduce overhead. Diversifying backend loads is another critical step, where heavy compute tasks are offloaded to cloud services rather than forcing local GPUs to handle everything at once. These shifts acknowledge that more storage does not solve memory bandwidth saturation. The solution lies in architectures that prioritize data flow efficiency and handle heterogeneity without crashing the entire service when a single node lacks specific capabilities or faces temporary throughput limits. The core lesson for practitioners is clear. System design for AI is dictated by physical hardware constraints, specifically VRAM bandwidth and CPU instruction set compatibility. Developers are currently building features based on the promise of infinite context that fail in production because they treat AI as purely a software problem. This brief teaches us that before scaling an assistant, engineers must audit for three critical factors. First, verify hardware instruction compatibility to avoid binary crashes. Second, implement graceful degradation strategies when bandwidth is saturated so users don't face hard timeouts. And third, design security layers that do not hard block users on minor configuration mismatches. Scaling AI isn't about adding more servers or hoping storage capacity will solve the problem. It is about immutable architectures and diversifying back-end loads to respect the physical limits of your GPU memory hierarchy. The gap between hype and reality exists because teams ignore how data moves through their hardware stack. When you understand that bandwidth, not just space, dictates performance, you can build systems that work reliably at scale rather than failing spectacularly when the context window grows too large for the available pipes. This is the difference between a prototype that works on your laptop and an enterprise system that survives in production. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.